Okay, welcome back, and now we're going to do another definition. This is going to be the definition of local extremum, okay, and meaning that we're also going to talk about local maximum, local maximas, and local minima, okay. So the definition, and then I'll make some notes. So definition 2, which is on this idea of local maximum, local minimum, and the idea of local extremum. So it says a function f has a local maximum at C if there exists an open interval I containing C such that I is contained in the domain of f. Okay, so this interval has to be in the domain of f, and f of C is greater than or equal to f of x for all x in the domain, or excuse me, in the interval I. Okay. Now, a function f has a local minimum at C if there exists an open interval containing C such that I is contained in the domain of f again, and f of C is less than or equal to f of x for all x in the interval I. Now, a function f has a local extremum at C if it has a local maximum at C of f or a local minimum at C. Okay? So if it has a maximum, if it has a local maximum or a local minimum on the interval at C, then we would say in general there's a local extremum. Okay? Now here's the thing. Again, we're looking at an open interval, right? And let's see here. Yeah. So we're looking at an open interval. Okay. So a couple of things to note about this definition is that a lot of times it's easy to pick out a local minimum, a local maximum. By the way, it's also, well, let me start over. One thing to note is that if you have an absolute maximum or an absolute minimum, an absolute maximum or an absolute minimum is also a local minimum and a local maximum. So if you have an absolute extremum, you also have a local extremum, okay? Because you can always take an open interval within the closed interval, okay? So that's one thing to note. The other thing to note is that it's easy to pick out local maxima and minima when you're looking at the graph, okay? Usually it's pretty easy, but sometimes it's not easy to pick out the local extremum. Because one thing, you might not have the graph, okay? The other thing too is when you're dealing with the endpoints, we don't talk about local extrema at the endpoints. When we're dealing with maximum or minimum values at the endpoints, we call those endpoint extrema. Okay, so just be aware of that as well. Okay, now if we don't have the graph, or if it's complicated, how do we determine whether we have local extrema? Okay. Well, that kind of brings up looking at the function. And how do we look at the function? Because we may not have the graph. Okay? If we don't have the graph, then we have to look at the function. So how can we use the function to help us determine whether there's local extrema and then find them? Okay? And that's going to be an interesting question, and that's where the idea of finding critical points comes in. Okay? So how do we find critical points for a graph? Well, that's where the derivative is going to help us. Okay? When we look at critical points are going to happen where the derivative of a function is 0, or where the derivative of the function is where it doesn't exist. And so if we can find those points, then we know something interesting is happening, right? We know if the derivative is 0 at a point, we have a horizontal line. We also know that from previous videos, previous discussions, that if we get a derivative function where at a point it doesn't exist, we know there's something interesting going on there. Maybe that's where a vertical line occurs, or a vertical tangent occurs, or something else is occurring. Okay? So that's what we're going to investigate next. Okay? Is this idea of critical points and then how to find them. Okay? See you next time.